I'm talking about completions. So why would you care for completions? It's a conference about logic. So if you have some axioms, you know, which says that A entails B, and that C entails D, and that E entails F, and then all the way above that is the weakest statement that true is true, and the strongest statement that the false is false. And then if from these axioms you derive, you perform some derivations, you want to derive what can be true if, let's say, A, C, and E are true, then this theory that you derive will be a lower set, of course. And you know, in a sense, all kinds of derivations that we do in math amount to completing something. You know, so for instance, in a sense, if someone gives us an axiom system or any set of entailments, we will present it as a partially ordered set, which I'm choosing now to denote by Q, because that will be useful. But let me make a nicer Q. And then, you know, this completion, the completion and the joins of this poset will be comprised of the lower sets, as I just said. You know, so they're going to be going like left, and the completion about on the meets will be comprised of upper sets, and then you can embed your partially ordered set into lower sets, into principal lower sets, and that embedding will preserve meets which may exist in your partially ordered set, and because they will become the intersections. And you can also embed your partially ordered sets into the upper sets, but observe that this is a contravariant embedding, because when A is less than B, then the upper set above A is bigger than the upper set above B. And here then the unions are preserved as intersections of these upper sets. But the funny thing is that you know, any joins that may have existed in your poset, any disjunctions that you may have made originally, any disjunctions contained in your axioms will be replaced by new disjunctions in this set of all possible theories that we may derive by disjunctions. For instance, if this Q is my rational numbers, then if I take the union of all sets below 1/2, it will be the open interval below 1/2, and if I take the join of rational numbers below 1/2, it will be the closed interval below 1/2. So it has thrown away the join which existed in Q and added a new one. And that is what bothered Dedekind. I mean, you know, he was kind of bothered by it, although he shouldn't, because all of these 15 years of work on number systems that he has invented, that he has invested before he published his pamphlet, were kind of work on the side, which wouldn't count as real math at the time, like much of Cantor's work didn't count. But so then he noticed then that if he maps each upper set to the set of its lower bounds, and if he maps each lower set to the set of its upper bounds, then he will get a closure, what we now call closure operator on lower sets, which will take any lower set into the lower set of all of its upper bounds. And similarly on the upper sets, there's a closure operator, which is interior operator in the opposite order, and then that is how he discovered, you know, these closed, these saturated lower sets or saturated upper sets or pairs, lower set, upper set, are what we call Dedekind cuts, and then that is how he defined rational numbers, and that is what we all studied at school. And then I guess MacNeille added his name by noticing that it all works also for arbitrary posets. So what you achieve is that if I give you an arbitrary poset where some disjunctions and where some meets and joins exist, or arbitrary axiom system which does involve some conjunctions and some injunctions, you can then complete it into the set of theories which preserves any joins and meets that may have existed and adds only those that did not exist. Okay, so then we go into the 20th century, and then in geometry, people notice that actually completions are needed not just to add these idempotent operations like meets and joins, but also to glue spaces. To you know, if we have spectrum of a ring, in order to see exactly what is happening with this ring, if it is not commutative, then we need to Grothendieck notices. Then we need to observe how exactly will some parts of this spectrum be glued over the open sets on that spectrum. And he starts his entire story about the sheaf theory, where instead of this poset, now we have the open sets of a topological space, and what was the lower sets will now become the category of sheaves, which are basically just, instead of completion under joins, they are completion under, as if were joins which remember how many copies of each leaf or of each neighborhood on this excuse me, on this spectral space they were, and that will be then local homeomorphism on the spectral space, which will be these étale spaces that people around Grothendieck spent 15 years studying, and observe that the topos theory then started as the theory of how we complete topological spaces. They are basically completions of the spectral space under co-limits, under joins which count multiplicities of leaves of environments above each environment. And there is still the same embedding, which still preserves any meets or projective limits that may have existed in the completion of the topological space, and topos theory started. And then in the early 60s, as all of this was going on, an algebraist like Jim Lambek said, well, I mean, this entire story about categories, it is about completions, and he worked out all kinds of completions of categories. And in 1962, I think he gave lectures at the ETH, and then that was the Springer lecture note in mathematics number 24, believe it or not. And that volume ended with Lambek's observation that actually, when you make the completion of your, be it spectral space or any category under limits, that you still have similar thing, but then these quote-unquote closure and interior operators give completely different things. You get the story about well, I'm not going to go into that, but a familiar story, how you reconstruct your ring from its spectra up there in the topos, and you get a completely unfamiliar and geometrically not very meaningful story at the bottom. And Lambek finishes his volume by saying, what under the sky does this Dedekind MacNeille completion, which is so valuable and so central in mathematics, and which is a central concept in logic, we are completing our theories under joins and meets, what does it mean in for categories, and what might the Dedekind MacNeille completion of a category be? And in 1972, John Isbell writes a fairly nasty paper. He says, our concern is Lambek completions, and proves that they don't exist. He shows actually that if you take the group Z4, and let me not spend too much time on this because you can kind of read it in the paper, but if you take the group Z4, then the completion under the co-limits, that will be its left actions, and the completion under the limits, it will be its right actions, and both are nice toposes, and they are there is an adjunction between the two of them. But because this thing is a group, these toposes are generated in one case, since it's generated by the co-limits, it consists of quotients of the co-powers of Z4. So that is these left actions of Z4. And in the other case, it consists of projective limits of the sub-powers of subsets of powers of Z4. And these are completely different things. I mean, limits and co-limits do not approximate the same space like in logic, joins and meets do. Not only, I mean, if we don't care for distributivity, we don't need the De Morgan. We're just saying, well, every lattice which is join complete is also meet complete. And for the categories, nothing can be further from the spirit of category theory than identifying inductive limits and projective limits. And so the door got kind of shut in a fairly user unfriendly way. And the message, like Isbell said, was largely the concern was negative. In the meantime, then, in the subsequent 50 years, people started calculating these completions in different ways. So on the web, the most used algorithm is singular value decomposition, which is kind of a completion under the eigenspaces. We're finding concepts in a data set as the directions in which that data set is pushing the basic vectors most. And then when there is a significant time series, for instance, in these news applications. So, Netflix problem was resolved by, Netflix problem is, if you watch a lot of Netflix movies, how do I best recommend, how do I best predict which movies will you like? So I need to mine from the movies that you have seen, mine the concepts of movies in your mind, although you will tell me that you may like comedies, but the word comedy means something else for everyone else. So data mining is done by a kind of linear completion in singular value decomposition. And then when there's a significant time series, such as the news application, so which news will interest you, then instead of numbers in matrices, we are interested in how are the items which are counted transformed. So the data have increasingly been structured in these prediction software as categories. And the same problem of completing categories while preserving what could already be derived in it re-emerges now from the applications. And although, you know, neither I nor Dominic, my friend who works at Apple, would ever be obnoxious enough to say, oh, let me go and solve Lambek's problem from 60 years and show that John Isbell was wrong, although we both like Lambek much more than Isbell. But somehow, you know, although you may or may not have any mathematical ambitions, the practice takes you back, and the question arises in new form. Sure, limits and co-limits do not approximate the same things, but in categories we derive things, and we are interested to know which operations approximate things both from below and from above. Those are the dominant concepts. This is the conceptual content of my category, which I have collected from the data. So the problem re-emerges on us again. We have an arbitrary category, and we have co-limit completion, and we have limit completion, and again we have these embeddings. Now here they are known as Yoneda embeddings, and we have these two extensions, and these closure operators are now, I'm just throwing these words. I don't know how many. I see that Andre is here. I hope there are more people who will know what is right Kahn extension and left Kahn extension. And then these extensions give us what are the closure operators again. And we've been struggling with that. And the crucial observation is that the adjunction is the wrong way around, which has been staring at me. I've been always kind of in the summer thinking about this Isbell problem without any idea, but at some point I noticed that actually the monadicity says that actually the category of coalgebras for this comonad and the category of algebras for this monad. So this is your saturated open sets and lower sets and saturated upper sets from Dedekind construction. So here we have this monad, and from monad theory, these are the final resolutions. The adjunction goes wrong way around of the two Kahn extensions, which has presumably hidden the observation from John Isbell, and it's a kind of not straightforward adjunction to prove. And the left Kahn extension now shows up on the right-hand side, and the right Kahn extension shows up on the left-hand side. And the crazy thing happens that 50 years of claims that the towers of these adjunctions of algebras over coalgebras, of algebras over coalgebras, which were always based on the claim made by Miles Tierney and Applegate in Battelle conference in 1968, that these towers go infinitely long before they stabilize, and they have been calculating these transfinite because they've been looking for stabilization in the form of categorical equivalence. It is in the form of an idempotent monad. However, the tower stabilizes at the first step if we just look at Cauchy equivalence, at monadicity. So these two categories are monadic and comonadic over each other, which means that they completely determine one another. And that was the crucial observation. So this is what we call the nucleus of the category C. And in general, there is such a thing, the nucleus of an arbitrary adjunction. So if we have a data matrix which is not stored in a category, but is data matrix over two things, it also has this nucleus. These two categories are not equivalent, as John Isbell has correctly proved, but these two categories are completely recoverable for one another, and they are indistinguishable by functors that are coming out of them and preserve their structure. So that if we form the suitable comma category of this adjunction, we will have a functor coming out of the original category, preserving all limits and co-limits, and it will determine a unique functor from each of these categories, and this will be then at least insofar as observable in terms of functors, this will be the Dedekind-MacNeille completion. This will be the category which preserves all limits and co-limits. Mind you, this is reasoning which is not up to equivalence, but it is up to surjection of functors. In other words, up to categories where everything is the retract of the image. And category theorists have been working up to equivalence, ignoring what they preach, that we should look at all objects up to morphism. So up to functorial distinction, there is a Dedekind-MacNeille completion. I'm not gonna go. I'm running out of time, and it is a fairly simple category which consists of pairs similar to Dedekind cuts on a categorical level. A nice thing that it does is that if one begins from a mathematical observation, if one begins from the category, from just generating the category of free monoids, multisets. So that is the free category with over one object with a byproduct. You can think of that as the categorification of natural numbers. Then you apply, then you can take some extension of it, and it becomes the category similar to Z, a category of free finite abelian groups. And then you apply something that they call the int construction, the integer construction, but for multiplication, and you get the category where the objects are the rational numbers, and the morphisms, it's a proper category, it's not a monoid. The morphisms are pairs of suitable matrices. Applying this construction, we get the category where the objects are real numbers. Morphisms are similar to what my talk is sandwiched between these two talks about bi-simulations as games. The objects are bi-simulations related to John Conway's strategies, the morphisms between real numbers. And the funny thing about it is that the byproducts in this category are the addition, the other way around. You discover the addition of rational numbers as byproducts in this free category, so that actually then these Kahn extensions become matrix multiplications. And then the Dedekind's question, how is the structure, how is the order and we would say topological structure of real numbers, how does arithmetic of real numbers emerge from that, gets answered in a very funny way by these operations, which are by these special suprema and infima, we're calling them, because that is what Lambek had proposed as the name for limits and co-limits, which did not get accepted. These suprema and infima of real numbers determine the addition of real numbers and discover for us the vector spaces of real numbers. So I'm going to stop there, and I'm sorry I didn't tell you more, but maybe I should be sorry that I told you too much. Thanks for listening.